Good afternoon. At this time, we welcome Jim Malley, who will talk to us about innovation and steel structure megaworks. James O'Malley, SE, is a senior principal with Degenkolb Engineers. He received both his bachelor's and master's degrees from the University of California at Berkeley. Mr. Malley has over 37 years of experience in seismic design, evaluation and rehabilitation of building structures, and is involved in the peer review of numerous innovative tall building projects. He was responsible for the analytical and testing investigations performed as part of the SAC steel project in response to the Northridge earthquake damage. Mr. Malley is chair of the AISC Specifications Committee and past chair of the AISC Seismic Subcommittee. Jim has served as a member of the board of directors and as president of SEAO-NC from 2000 to 2001 and SEAOC from 2003 to 2004 and NCSEA from 2010 to 2011. Mr. Malley was also a member of the board of directors and vice president of the EERI and is currently president of the board of directors of the Applied Technology Council. Thank you for joining us, Mr. Malley.
All right, well, let's get going then, thanks. I really appreciate the opportunity to speak with you today about innovation in the design and evaluation of steel structures. So, table of contents, we'll do a quick introduction, and then I'll talk about the areas that engineers can be innovative when they're working with steel structures. So architectural design configuration, some discussion about system selection, about high performance products, and then talk about analysis techniques and modeling and some connections. I want to talk a little bit about existing steel structures because a lot of the innovative work that we're doing these days is on seismic evaluation and retrofit of older steel structures. I'll talk a little bit about how codes and standards and guidelines work into being innovative in steel design. And then I'll share some example projects, a couple of, or one of my projects, and then a number of projects that I've peer reviewed. And then a little bit on what are the opportunities, when do you have opportunities to be innovative? And then just some summary and conclusions. So with that, we'll move on to the next slide. Okay, so steel structures go back over 140 years in the United States, and obviously there's been a lot of progress on what we do with steel design with today's technology. There you can imagine we do things very differently as far as how we connect the elements together and fasten them. Used to be with rivets, then bolts and welds, and now we even have robotic welding. So there's also been great improvements in the material that we work with. The steel is much cleaner, they could call it these days. It's stronger, it's more ductile and very consistent in the products that we get today. And then there's equipment advances. I put a picture of a crane there. It's interesting about how important the crane is to how the building gets built. And really it should be also considered in how we design structures. So working with the contractor on the equipment that they're going to have access to on the project is also quite important. So we also know a lot more about performance than we have than we did in the past, and that comes from analysis techniques and tools that we have today, as well as testing and research that's been done over the years at universities around the world, and also obviously going to see earthquake performance when we do have earthquakes. The picture on the upper right is from San Francisco after the 1906 earthquake and the 1985 Mexico City earthquake. This is a picture of the Pina Suarez towers that unfortunately had some catastrophic collapses. And really, those kind of events really do push us forward and to make changes and to innovate and to improve our practices. Okay, so where can innovation occur? I mentioned the 5 areas here, so we'll jump right into the first one, which is architectural forms and design. So obviously architects are getting more and more ambitious creative with their forms. You can see a Frank Gehry project on the bottom left, a museum, very, very complex shape. Obviously, to hold the structure, to design a structure to hold that out is not as easy as a rectangular box. You can see a couple other tall buildings, one in Seattle on the top in the middle, one in San Francisco down below that. A VA project that I designed, that'll be the next slide. We'll talk about that as far as configuration issues. And then finally, a project that I'll talk about in one of my peer reviews at the end of the presentation. So the VA hospital that we designed in Las Vegas is one building, one very large building over almost 1 million square feet. And but it was had various story heights or numbers of stories. So the green, the darker green were 2 one-story buildings, and orange are the 2 3-story buildings or structures, and then a 7-story structure in the middle. And if we had tried to tie this entire facility into one building or one structure, it would have been very complicated to design the lateral, the seismic system for that kind of a building. So what we decided to do instead was to break it up into smaller, regular, rectangular shaped structures. And in the boxes here, hopefully you can see my cursor. You can see dark line or dark dotted lines where we broke the building up. And so the intent there is that each of those act as individual structures. So when the earthquake hits, and here's a simulated earthquake for you, you can see the buildings will respond to the earthquake on their own and hopefully have much better performance overall. So let's talk about systems. In our US building code, we have, believe it or not, 82 different structural systems listed. Concrete, steel, wood, masonry, all kinds of different configurations and types. There's a lot to choose from. Really only a handful are used on major structures at the present time. So new systems are really based on a combination of research and validation through and economic factors. So analysis techniques and then economic factors drive new systems. And some of the ideas, obviously, for engineers will come up with an idea, and it may lead to a new system eventually ending up in the building code. So I'm going to talk about some of the more recent code systems that have been developed and added in the steel area. The first one are what we call steel plate shear walls. This concept was originally developed in Canada, and we have some Canadian engineers working on our committees, and they brought this forward to us to start to develop that system in the US. So the idea is essentially to put a thin steel plate in the boundaries between beams and columns in a steel frame, and then it acts sort of like a shear wall, like we usually would think of in reinforced concrete. That they can generate tremendous amount of strength. This is a test on a picture on the right at the end of a test at UC Berkeley years ago. And you can see that the plate itself, is being very thin, will buckle during the seismic response and orient itself as in what we call tension field action, depending on the direction of the lateral load. And it can be a very effective system. I'll show you an example of one of those on a large project in Los Angeles later in the talk. So designing those systems, usually it really is just a free body diagram for those of you in the audience, that you can design all the elements to deliver the forces between the plate element in the middle and the column and the beams to the columns to each side and the beams above and below. And you can basically walk your way through the design of the building in that fashion. One of the things that we found in designing these steel plate shear wall buildings is think about the fact that the plate thickness that's available to us is not, just goes in steps, if you will. You might have like 1 centimeter plate, then a 2 centimeter plate, and a 3 centimeter plate that's available to you. And very often the plate thicknesses do not have to be very large. 2 centimeters is actually quite a large thickness for these plates. There's the strength of the plate is obviously proportional to the thickness of the plate. And so what we found was that when you design this system, when you use solid panels, it can create very large additional demands on the columns in the building and the foundations. And so some researchers developed an idea to put holes in the plate to reduce the capacity and tune the capacity better to what the seismic demand on the entire building would be. So this is an approach that's also available to us on steel plate shear wall design. Another kind of system that we work with are composite systems, and I call it the best of both worlds because we can use the steel where it is most effective in tension or in shear, where steel is very ductile and has good strength. And then the concrete, primarily in compression, where concrete is really efficient. So there are numerous options of that system. You can see some examples here where on the upper right, you've got a sort of a braced frame configuration where the braces and the beams are structural steel and the columns would be a composite element between concrete and steel. And at the bottom, you can see, and imagine a concrete shear wall where you would have coupling beams between the wall piers that you would use a steel coupling member instead of a reinforced concrete coupling beam. So one of the very new systems that's been developed in the US is called a composite sandwich wall. And the AISC has dubbed this speed core. So if you wanted to Google speed core, you would find a lot of information on this. This system was originally developed for the nuclear power industry in the US as a sort of a modular type system, but it's been passed over to the sort of traditional buildings as well. And what the idea is basically to use steel plates, you can see at the bottom in the middle there, and then inside the steel box, pour reinforced not reinforced, just concrete. There's no reinforcing bars in these walls. There are tie bars, which you can kind of see in the picture at the bottom, that are at very closely spaced centers, usually on the order of 1 foot, about 0.3 meters spacing in both directions to keep the wall plates together. And that acts as your shear wall. And where we've seen this is potentially applicable is to replace reinforced concrete, what we call core walls in tall buildings, where traditionally in a very tall building, the architecture or the design would want to have steel framing for the floors, the beams and columns, but then use the core concrete shear walls around the elevator shafts and stairs at the center of the building, for example, in an office space. With the speed core, we can avoid the interaction between the concrete elements in the core and the steel elements and just make it basically an all steel building. And that has some real advantages for speed, and that's why they call it speed core. On this example project that was done in Seattle that I'll talk about a little later as well, they were able to save over a year in construction out of a 3-year process. So it's very significant on how fast they could build the tower. So AISC is really pushing this forward for some of these larger projects. So that's kind of where we're at on some of the more innovative systems today. But what do we think we're going to see over the next maybe say 20 years in steel? So one of the ideas that has been coming forward is there's concern about in our typical designs of structural systems of all types. There's no real code requirements about making sure that at the end of the earthquake, the building has come back to plumb, so straight up and down. Potentially, you could end up with a building that's leaning, and after the earthquake, and obviously that would be very difficult to repair, so that might have to be torn down. So there's been some movement in the profession to try and develop systems that are what we call self-centering. And there is in our gravity systems, and gravity will help to potentially self-center, but if we get very large earthquakes, it may not be able to do the total job. So what these self-centering systems use are post-tensioning in most cases to basically pull the building back to plumb and vertical. So in the upper right, you can see a brace frame example where in between some vertical post-tensioning that goes on in the two between the red bracing on either side of the center of the system, kind of in this area here and here. And so that's an element, a way to self-center. On the bottom part of the system is a moment frame system where we've got horizontal post-tensioning bars, again, that will do that pulling back or recentering the building after a major earthquake. Another approach, which is a little less direct, is a rocking system. And this has been actually studied for many years. There were tests done back actually in the 70s, where on a shaking table where a steel building was placed without any connection to the table and allowed to sort of bounce around and rock. And you can imagine there is stability in the system just from the kind of the gravity that goes on. So, but really we don't have any rules in the code about how to do that. There's some work that's going on to try and develop those. Some engineers have been using some systems like in the little graphics at the bottom there, with a piece of angle that's bolted to the foundation and then bolted into the braced frame, that would allow those angles to rock, or the building to rock up off of those angles. And but we really need to control that. So there's some more work that needs to go on before something like this would be codified in any sort of fashion. So the next step is partially restrained moment frames, and that system is actually, I don't know that it's that innovative. It doesn't get used very often in modern practice. Usually with our seismic systems, we want the connections to be stronger than the members, and don't want to get the ductility out of the system in the connections. But in the partially restrained design approach, we actually want the connections to be yielding. And what we have to make sure is that we control the failure mechanism to be a yielding mechanism rather than sort of a fracture type situation. There is a proprietary system on this that is shown down at the bottom here, put together by, excuse me, one of the, forget the name of the company, but and I'll come back to me shortly. But anyway, it's a pretty innovative system where they use some bolted connections and friction plates to generate the partial restraint or partial Simpson Strong Tie is the name of the company that developed that system. Okay, so we'll move on now to the high performance products. And I think we all know that generally our building codes focus on life safety, and we also, but there's only limited emphasis on functionality and repairability after major earthquakes, except for our critical post facilities such as hospitals, which we really want to make sure are occupiable after an earthquake. We recognize that some owners are interested in making sure their buildings are functional or have limited damage after an earthquake. Think about data centers or critical manufacturing facilities or museums. And museums are an interesting case because the contents are potentially so fragile and expensive, billions of dollars in museums, that making sure that that building has limited damage and shaking is very important to protect the contents of the building. In California, we've been talking about what we call post-earthquake resiliency recently. where we want to make sure that our regions, if we are subjected to a major earthquake, will be resilient, and there won't be a disaster like which occurred in New Orleans after the Katrina hurricane. So that's another area where we might want to look at using high performance products. And those generally are a couple of different things that we use: seismic isolation and damping. We call this response modification. Basically, those types of elements change the response of the building so that it reduces the demand on the rest of the structure, limiting any kind of damage that might occur, and dissipating the energy of the earthquake and taking sort of the demands out of the primary structure. So both of those require us to have a lot of data and information, laboratory testing on those special elements or devices. And we really need to have a good representation of what we think the maximum earthquake shaking that's going to occur in those buildings might be. And usually, again, these would be implemented when we're going potentially beyond the code minimum or just life safety performance. So an example of seismic isolation here. So as we know, the ground shakes. If the building is attached rigidly to the ground, it has to take the motions of the ground. But if you isolate it, you will have the ground move, and essentially the buildings stay in place. A lot of times this is like a friction pendulum isolator is a very common system for seismic isolation. So we'll talk about damping. Can get very good for high performing buildings out of dampers. It helps to reduce accelerations, to protect the contents, maybe not as much as base isolation does though. And the cost increases are fairly moderate, a few percent of construction costs potentially. And it's actually getting pretty widespread application. There's a couple of different types here. We actually usually work with viscous dampers, using viscous fluids as part of the damping element. In the center, that graphic is a friction system where basically friction between plates is where the energy is dissipated. So a little bit more on dampers. The upper right corner are what we call piston dampers. These are very similar to shock absorbers in your car. To limit the movement or the deformations. They can get very large. The ones in the center graphic at the top were actually used on ships for missile launching, so that they wouldn't damage the ship when the missile launch went off. We don't use dampers quite that big in buildings, but we do get up to up to 500,000 pounds of force in some of these dampers. And the bottom part of the graph is what we call a wall damper system. And you can see on the lower left there, this is what the graphic looks like in the center. The idea here is that you have a steel box that is filled with a viscous fluid, and the viscosity of it has been kind of likened to cold peanut butter. So peanut butter when it comes out of the refrigerator, if you will. And so that box is filled with that fluid, and that's connected to the bottom of the story. And then a steel vein is placed down into the fluid, and that vein is connected to the top of the story. And during the earthquake, we get drift or motion between the two floors, and that pushes the vein through the sticky peanut butter and dissipates energy in that way. So it's a very slick sort of system. We implemented it on a hospital in San Francisco on the lower right there. First time it was used in the United States, and worked out very well. It actually saved money, almost $10 million in the construction costs of the hospital over a standard steel frame building. Another a system that we use or a modification device is called a buckling restrained brace. And you can see the graphic here at the top, and I've got a little demonstration here with a straw. If in a regular brace frame, when we put that in the brace in compression, we buckle it over the length. Hopefully you can see that here. But if we restrain, and I'm going to try and restrain this one at the center point, the capacity of that brace goes up dramatically. And in the buckling restrained brace concept, you basically put the brace inside a retaining tube, and you can push it so that it will have the same capacity essentially in tension as it does in compression, because it's not allowed to buckle. And that makes it a much more ductile brace. If you have a regular brace and you cycle it a number of times, after a few cycles of large compression and buckling, we'll often lose the capacity of that brace. And this is a much better system. It's very widely used in the United States now on major buildings. And there's some additional concepts of what we call the strong back, where you combine these buckling restraint braces with a stiff spine to get the excellent seismic performance. So there are other ways to use ductile elements like buckling restraint braces or dampers, rather than just as sort of diagonal elements in frames. We can go across building joints or between buildings to dissipate energy and reduce the deformations. And then there's a thing called an outrigger that I'll show you I'll show you an example of these in the next couple of slides. So here's one where we've got a damper element across a seismic joint, and when the earthquake comes, you can see motion back and forth that pushes, and that will dissipate some of the energy and help, and as well as help the buildings from pounding together. So this is a way to have smaller seismic joints as well as some energy dissipation. The outrigger idea, this is a good example of this. Another project that I peer reviewed was on the Wilshire Grant project in Los Angeles. And the lateral system on that building in the short direction of the building, the transverse direction in this direction, was just the depth of the core. And that was the ratio of the height of the building to the depth of the core was on the order of 15:1. And high-rise designers will tell you that that's not going to be a building that works because it's going to be very susceptible to wind motions as well as earthquakes. And so at that point, you go to what we call an outrigger system, where you grab onto the perimeter columns of the building with these diagonal outriggers. And in this case, we had three sets of them because the building was so tall. And it essentially gives you a wider base to resist the seismic motions. And that creates a much better response of the building, change the period down from 11 seconds to 7 seconds, and really makes the lateral system much more efficient. In that same building, in order to use what we call belt trusses around the perimeter of the building, and so you can see those graphically here on the slide on the right with the red box, and that basically grabs essentially all of the gravity load of the building to resist the overturning moment from either wind or seismic forces. So it's a very again, makes good use of the steel, reduces the amount of tonnage, and obviously reduces the demand on the foundation. So another kind of neat element that we can use on projects now is a composite floor system element called SPS. This was also developed in Canada, and almost all steel frame buildings, the floor diaphragms or floor slabs are in the U.S. come from metal decking that then has concrete poured on top of it with some reinforcing steel for the concrete slabs. In this case, this is a composite system with two steel plates with a polyurethane elastomer core in between, and then that basically spans to the beams in the floor system. So you wouldn't have any concrete for the flooring. The elastomer provides sound control, vibration control, And it's been used in, a couple hundred projects, in a number of them in some buildings and bridges, as well as a few stadiums in the United States. So then what about another idea for products or specialty elements are multi-component braces. And again, this is from another peer review that I did. And I'll show a little bit more about that later. But the braces in this building were connected to the structure at only at 18 floor increments. So it was a 54-story building, and there were 3 braces on each side of the building. So those, and what the engineer did was to put a buckling restraining brace at one end and a damper at the other end. And the damper was there for wind control because there were condominiums at the top of the building, and the owners of the condominiums would get seasick in decent sized windstorms if they didn't have some additional damping. Excuse me. But for the seismic response in a major earthquake, those dampers will lock up, and then the buckling restrained braces will yield and dissipate the energy. So again, very interesting type of approach on a unique project. Okay, so let's talk a little bit about structural analysis. And so some advanced techniques that we have for capacity design, nonlinear analysis, ground motions, and soil structure interaction, and then some modeling techniques. So when we talk about capacity design, what we're interested in are thinking about using fuses in our building to kind of limit the amount of force that goes into the building in the earthquake. And this is sort of similar to what happens in a residence or your house with your electricity. In your fuse box, you want the amperage of the fuses to be less than the amperage of the wire, so that you don't overload the wire and the fuses blow, but not the wire, which if the wire blew in the system on the right, you might burn the house down. So similar in earthquakes, earthquake design, we want to have fuses in our building to reduce the design force and build ductility and deformation into the building with elements like those buckling restrained braces that can dissipate a lot of energy. So that's kind of the concept on capacity design. Then once we know the strength of those buckling restrained braces, we design the beams and columns and foundations to be strong enough to make sure that that's the yielding element in the system when the earthquake hits. So a lot more nonlinear analysis is used these days, a lot of it on tall buildings. That gives us a much better understanding of the performance of the building than our typical, linear elastic type of analysis techniques that we use. And there are a lot of ways to model these, and you need to, when you're doing a nonlinear analysis like this, any element that provides stiffness to the system needs to be incorporated into the model. So there are some various options for modeling the nonlinear behavior of the elements in the system. These are some different options that are in some guideline documents. And these are based on some test results from laboratory tests of different elements. The horizontal axis would be the deformation in the building, and the vertical axis, or in the element, and the vertical axis would be the force. So as you cycle back and forth, you would be able to see this type of deformation, and then you could model the test results in your computer model using some techniques like this. So response history analyses, we a lot of times now we actually put simulated ground motions into our models. Whenever we can, we use recorded motions that match a response spectrum, which is the graphic there on the lower right. When we don't have ground motions that can simulate the motions we think the building might be subjected to in the future, there are techniques that seismologists can use to simulate those motions. And one approach where this comes into play is in the Pacific Northwest, where we have the Cascadia subduction zone. that can generate magnitude 9 type earthquakes. And so we can simulate those results for the city of Seattle, for example. Just want to note that there's a lot of uncertainty in our characterization of ground motions. So we run multiple simulations, oftentimes like potentially 20 or more ground motions through our models to try and understand the performance. Something else that we sometimes use is what we call soil foundation structure interaction analyses, and that would be the graphic on the right, where we might develop stiffness springs to represent the soil that surrounds the foundation of the structure, and then shake the bottom of the rigid box and use the stiffness of the soil to interact with the superstructure to get a better approximation of the performance of the building. So BIM modeling is in building information modeling. I think there was another presentation on this at the conference. Is it's something we're doing all the time now, and really gives us the opportunity to work very closely with the fabricators and erectors of the steel buildings to make sure that our design techniques and the way we model them in the computer is consistent with the way they're going to build them out in the field. So it really gives us a great way to work in close context with the contractor that's going to build the structure. So let's talk about connections. So obviously very important for the performance of the building, and so we really want to make sure that generally the connections are stronger than the members, as I said before. We now are sort of pre-qualifying connections based on testing and research to make sure that we understand what the performance is going to be. We also sometimes use castings for very unique conditions, and I'm going to talk about a special case of column splices. So on this conformance demonstration for these pre-qualifying these connections, we start out with developing some test specimens that simulate the conditions of the connection, and then build a test setup like in the lower left, put it through a lateral or cyclic force or deformation procedure as shown in the upper left, and then we get the response down in the lower right. We also need to simulate the performance in our computer using what we call finite element analysis, and you can see a comparison to a test and a model there. So those things all go together to help us write the rules for these pre-qualified connections. There's a number of them in our AISC standards. There are a couple that are what we call proprietary, that were developed and patented by a company. One of them is side plate here. So if you wanted to use this connection, the fabricator would have to pay a fee to side plate for this technology. A similar one is what we call Connects Tech. This is uses tube columns that are filled with concrete, and then brackets that are bolted to the four corners of the tube, and then another bracket that's welded to the end of the beams that frame into the connection. And then everything is bolted together in the field. So no field welding in this detail. And there's a connection test result there at the bottom. So that's another proprietary pre-qualified connection. And on castings, the idea here is a couple different applications. On the lower left is a very unique structure in San Francisco. It's a transit center that had some very long span, very large, almost like offshore platform type construction. And in this case, it was very repetitive because the building is 4,000, it's over 1,000 meters long. And so the contractor decided to go to a casting company that would make molds of the steel that they needed for these connections, and then cast them, bring them to the site, and then use that as part of the connection between the major elements of these trusses. Another option for castings is the connection element itself. And in this case, it would be this part of the system where you would have a tube brace here, a circular brace. And there could be a catalog of these depending on the size of the brace as to what the capacity of the connection needed to be. And you could use it sort of have a catalog and just to kind of specify that for whatever size brace that you have. And then there's also castings and other ways to we make what we call replaceable connections. So the idea here is if after the earthquake, if this connection might have used up all of its energy dissipation capacity, but we could then unbolt it and bolt in a new replacement brace for when the next earthquake might hit. And so there's some various configurations here. Some of them are using yielding of plates, like in the lower left, but the one in the lower right is one that relies on friction between various plates in the test setup or the connection setup. So partial penetration welds are in column splices can be a challenging thing for engineers. In our standards, we primarily want to use complete joint penetration welds for these to make sure this is a very important connection to make sure that we keep stability in the building during an earthquake. The problem is that's a very challenging thing for the contractors to build, because imagine this is what's shown here is a partial penetration weld, but a complete penetration weld would have the weld coming all the way across to the other side, and basically the top piece of column would have to land, it was cut down to like a knife edge, and then dropped onto the lower column. And so that makes it very difficult for the contractor to control the piece of steel, 30 or 10 meters long, maybe 500 pounds per foot, and get that in place and then try and weld it. So they really would rather have some little bit of ability to use a partial pen weld. So some research was done on this, both analytically and in a laboratory, to develop what we call a heavy partial joint penetration splice detail that can give us the similar performance to a complete penetration splice. So another kind of innovative detail for a connection. So let's talk for a couple minutes about existing steel structures. Generally, steel buildings have performed pretty well without any collapses, but we did have the Northridge earthquake that did damage that we weren't expecting, and really led to a lot of research and testing and the like that then led to a lot of innovation and new tools for us. And when we work with existing buildings, we're dealing with some of these fracture issues that we found in the Northridge earthquake, and the modeling therefore becomes much more complicated than it would be for some of our new building designs with ductile connections. So some slides from the Northridge earthquake. I'm in the dark here, aren't I? Where so a lot of buildings had fractures. You can see in the graphics here, fracture through a column almost to the other side of the column where the beam flange pulled away. Here's a piece where a piece of the column flange pulled away with the beam flange. The one building was torn down here on the left, which was kind of a low-rise building, but it did have that residual displacement I was talking about before of about 4 inches in the first story. And basically the building had to be torn down because of that. So we're trying to avoid those sorts of things. So what we found in studying this connection that was very commonly used, it was called now the pre-Northridge connection, is that it had a number of problems in it. That the connection geometry was not the best. It created some very high concentrations of stress and strain demands that would lead to fracture. We didn't really have good control over the material properties at that point in time. And there were some issues with the welding procedures, and some of it was the toughness of the weld material wasn't controlled. Now we have much tighter control on that. The techniques and the inspection were also kind of lacking. So there were a lot of changes that had to be made on these steel systems that came out of the Northridge earthquake damage. So when we talk about retrofits, we really do have to be very creative, because we're really looking at existing construction. So we have to work with the parameters that are already in the building. It's not like new design where you can work with the architect to come up with the best structural system. You're going to have to really use advanced modeling techniques to try and capture some of these situations. So the buildings are quite sensitive to ground motion. Acceleration records, what we found, because of the fracturing. These are 5 different ground motions. You can see on the right for the same building, theoretically for the same size earthquake. And you can see on the left the difference in displacement. So one of the buildings on the lower right there was probably pretty close to collapsing, whereas some of the other buildings didn't have much damage at all. And that's all just because of the difference in how the ground motion hit the building. We also found that in many cases, the demands on the building do not go over the entire height of a taller building, but really focus themselves over maybe 10 to 12 stories. And again, that focusing is where we could really have some problems with the fracturing of these connections. So another thing is on the column splices. Again, these column splices were partial joint penetration welds with not very high toughness. So they are also susceptible to fracture. And we can see with variations in just varying the toughness by maybe 10 or 15 or 20%, you can see very different performance in the building. So the buildings get very sensitive on these existing buildings. This is a retrofit that graphics of a retrofit that we're about to complete in San Francisco. And I put this in because it was very interesting that the owner, we actually ended up having to have 4 separate phases where we added viscous dampers and did connection strengthening. And rather than starting from the bottom and going to the top, which would be the most logical way to do it, we really, the owner didn't have control over the office space and when the tenants leases would be up and they'd be changing tenants. So they wanted to see if we couldn't sort of hopscotch up the building when they had opportunity to get in and do the work. And we were able to convince the city of San Francisco that the building was getting better and more seismically resistant at every step along the way. So we actually had to analyze the building for each phase of construction that has occurred over the last 5 years or so. So it's kind of an interesting approach. All right, let's talk about codes and standards. So generally, the building codes are quite prescriptive. They tell you, how you should design a structure to just meet the intent of the code. So in some ways, it does stifle engineers from innovating, but there is language in the code that allows us to demonstrate equivalent performance without using all of the prescriptive requirements of the building code. And this is some of that language. So where it says an alternative material, design method, or construction shall be approved when the building official finds that the design is satisfactory and complies with the intent of the code. So that's sort of general language, but there's no guidance in the code on how you do this. So what has happened in the US is to develop the development of these guidelines for what we call performance-based seismic design. There are a few of those out there. The 2 most common are on the left or on the right side, the Pier Tall Buildings Institute guideline, and then the Los Angeles Tall Building Structural Design Council guideline. So performance-based earthquake engineering is being widely used on these projects, and as well as in design of new tall buildings. And it requires nonlinear response history analysis, and also what we call peer review, because when you do something innovative, it's not 100% sure that the engineer isn't going to miss something in the design. So having another set of eyes to review the project of another expert in the field, it gives the building department the confidence that yes, we are getting at least equivalent design, if not better. So let's move on to example projects here. I'm getting close to the end of my time. So wanted to go through a few of these to demonstrate some innovation that's gone on a lot of tall buildings and complex buildings, and usually all three. And as I mentioned, peer review is used on all these. First one I'm going to talk about is a project that I was the engineer of record on in Oakland, California. It's a retrofit of a 15-story, one of these pre-Northridge moment frames for the California Department of Transportation. And so it was built just before the Northridge earthquake. It has those vulnerable connections. So the building is occupied by a large number of engineers. They're bridge engineers, not building engineers, but they were aware of what happened in the Northridge earthquake, and they got some money together from the state to do testing of the connections that are used in that building, because they're quite large, much larger than any of the testing that was done in the research right after the earthquake. And what we found was not very good performance, and some fractures in the connections, and not very much energy dissipation. So that's what sort of led to this retrofit project. And here I'm going to show you some video of some of the tests. You can see fractures. Here, there's a fracture there. Now you're also bolts that are breaking, and these little drops with front, or whenever one of those bolts would break. So when we got this commission, we looked at 4 different schemes using the kinds of techniques that I talked about earlier. One was fixing the connections. One was adding dampers and fixing connections. One was a whole new lateral system using buckling restraint braces. And the fourth was a base isolation approach. So we went through a decision process with the owner and came up with a connection modification, and dampers being the best approach. So this is a graphic of how we did this. With the diagonals now are the dampers that went in, and you can see connection retrofits here at wherever you see sort of those bold things in the elevation. This is sort of graphically what these look like. The connection modification, connection, and then between the dampers and the frame. So we had to simulate in our model these existing connections that were fracturing in those test results that I just showed. And we use what we call a fiber model, where we would put a fiber, kind of like a string, if you will, at the location of the beam flanges, as well as one each at each location of the bolts. And then we tune those capacities to be similar to the capacity of the member. And we were able to simulate, as you can see in the graphic at the top, the model is in red and the test is in blue, and we were able to simulate the fracture and even the bolt breaking in our model. So that was very helpful to us as we analyze the entire building. Here's a graphic to show the model, and on the left is the retrofitted building. On the right is the existing building going through the same ground motion. And what you'll see is when the motions get large enough, you'll see some red going. Here comes the red on the right. And that is simulating fracture in those connections. And it continues and gets a little worse here, where almost the entire building has now broken the connections, and it's not clear that that building would have survived that earthquake. On the left, you can see much less damage. And we use this to sort of tune how much retrofit we did, where we fixed connections, and how strong the dampers were. So because the connections were so large and the existing response of the testing was so bad, we convinced the owner to do a full-scale test program on some different ideas and some concepts here that you can see 4 different ideas that we tested. We simulated both the initial welding of the connections together, as well as the retrofit welding over on the right-hand side. And because the frames are along the perimeter of the building, we only had limited access on the outside next to the curtain wall or the glass for the edge of the building. And so then we simulated that welding at a test setup at UC San Diego, a full-scale test where we pushed across the top, and then tested the connections. We also did finite element analysis to simulate, and our tests and the model simulated quite well, so we felt very good about our analysis technique. Okay, so now some other example projects. This is a museum in San Francisco that had a very, and again, base isolated system, very, expensive contents, very complicated building design, and lots of innovative things happened here on the right. Middle is a very, like a 50-foot, so maybe 16, 17-meter cantilever over a place to eat lunch outdoors. So interesting project there. This is the very tall steel plate shear wall building in Los Angeles that I mentioned. This is the tallest of these steel plate shear wall buildings in the world. Very large box columns and very thick plates. So very complicated design to review and to look at. I mentioned the Wilshire Grand project. It's actually the tallest building in the United States west of Chicago at 72 stories. We talked about those outriggers. One of the other things that was interesting about the project, it's on what we call a mat foundation. That foundation is almost 7 meters thick over essentially the size of the building. And that was one continuous concrete pour of over 2,000 truckloads of concrete in order to pour that mat foundation. This was that project in San Francisco I mentioned with the exterior bracing, three giant diagonal braces on each side of the building. One of the other interesting things that we did, or that the engineer did, was to allow some uplifting at the corners, the corner columns in the very largest earthquakes to sort of reduce some of the demand on the foundations. So there was a mechanism to control that in their design. There's the project in Seattle, the Rainier Square project that I showed with the Speed Core system. Again, very exciting new project to be able to implement and see the results and the speed that the building was able to be built with. Here's the last of the examples. This is a quite different building. It's being built right now near the Los Angeles airport. It's about 2 miles from a major fault. Basically, it's called a wrapper because these steel boxes sort of wrap the building, kind of like the bird's nest in the Beijing Olympics. If you remember the stadium in the Beijing Olympics, that kind of approach was used. We were lucky to convince the engineers that base isolation was really the only way they were going to demonstrate this building would ever work. And so it's under construction right now. So it'll be very interesting to see how that does in a future earthquake. So just wrapping up now, how do you get the innovation mindset? You have an owner that wants to do something special, tall, configuration, etc. Maybe you want post-earthquake functionality. You want to kind of go beyond something that's and use something that's not required in the code, like avoiding residual drift, or when there's a lot of money to be saved by using some of these innovation technologies. And again, hopefully someday when the community wants to have a resilience in their design procedures. So lots of ways to deliver innovation on steel projects, driven by technology and many other factors. Lots of examples on recent projects, and hopefully we'll move toward resilient communities. And usually the costs are not too bad, the additional costs of doing these sorts of innovations, except if you get into very unique architecture. So with that, sorry if I went a little over, but I thank you for your attention.
Thank you very much. Agradecemos a Jim Malley por su exposición. Pasaremos al espacio de preguntas y respuestas. We thank you, Jim, for this presentation, and we will continue to the questions and answers session.
Okay.
The first question is from Professor Luis, and it's, what is your opinion regarding spectral matching
and conditional spectrum. Do you think that the spectral matching is valid if you're trying to estimate rare responses, like collapse, instead of the mean response? And what about bidirectional analysis? How do you select them?
Great. It's a great question. So yes, I'm not a real huge fan of what we call tight spectral matching, where you're really trying to, and I get it's probably, I can go back to that one slide, but it's probably take too long to get there. But so yeah, I think it's concerning about just exactly what you said. Sort of the uncertainty kind of gets taken out of the ground motion suite with spectral matching. So there are actually penalties in the guidelines if you want to use the spectral matching approach. Conditional mean spectrum is very widely used now, and usually we have two different sets of ground motions, or two different periods or period ranges that are used for the conditional mean spectrum approach, and that's pretty widely used now. So not so excited about really tight spectral matching. Much more amplitude spectrum or scaling is a much better procedure, or maybe some moderate matching, and then conditional mean spectrum is actually widely used.
Thank you very much. The next question we have is, what is your opinion regarding spectral matching and conditional spectrum? Do you think that spectral matching is valid if you're trying to estimate? Oh, wait, is that?
Yeah, that's the one I just entered.
Oh, that's the same. So sorry. One
problem.
second. It's twice. It's been, yeah, sent twice. Okay, here. Which of the types of damping you mentioned is the best, or how do you decide which of those to use?
Yeah, good question. So the primary one that people use in the US is viscous damping. And very, very often it is that piston damper, kind of like the shock absorber. It looks almost like a brace. And that's heavily used and widely accepted. They have lots of examples and tests. The wall damper was a good option for this one project that we did. A lot of it because of the architecture of the building and how we could place the wall dampers and not impede the architecture of the building. The wall dampers also have potentially a very high capacity. It's even higher than the piston dampers. Friction dampers don't get used nearly as much. There's some concern about the long-term viability of the friction surfaces. Say you put those in a building and they clamp it together, and then you wait for the earthquake and maybe it doesn't come for 50, 60 years. There's some concern about like metal bonding, and you may not get the friction that you think you're going to get. So that's really a lot of times why the friction is not as widely used as the viscous approach.
Thank you very much. The next one is, it's in Spanish, so I'm just going to translate it a little slowly, but here it is. It's, how do you decide what type of device of control you use in a building that's tall? As an example, BRV, shockers of friction, or viscosity shockers? Yep,
that's the viscous dampers, yeah. Again, it depends a lot on the overall configuration of the building. We are doing a number. I didn't show any of those yet because none of them are in construction yet. But I'm peer reviewing 3 or 4 projects right now that are in the 40-story range where they are using just BRB braces and not with a perimeter system, rather than sort of the core type system. It depends on the architect. So the architect has to sort of buy in on external braces. Some would rather keep the braces hidden in the center of the structure, and that might lead to a different approach. So yeah, a lot depends on the architect, the architecture of the building, and kind of that back and forth, the interplay between the design professionals as far as how to select the best system.
Thank you very much. The next question is also in Spanish, and I translated it. So if something's wrong, I can try to look it up. What are the advantages of steel coupling beam when the core is made of concrete walls? This is in relation to a specific coupling beam. What are costs increasing? Is manufacturing complicated? Is ductility increased? This is from PH Hector Davalos.
Okay, that's a good question. Yeah, so the steel coupling beams, if you've ever done or seen a reinforced concrete coupled shear wall building, the reinforcing that has to go in the coupling beams is very complicated and can get very difficult to place. And sometimes the concrete doesn't come out that well unless you have some really special mix designs and super plasticizers to make sure that it'll fill into all the spaces. The idea then, and especially if you get into very high demand coupling beams, that's when a steel beam might make some sense. And the idea is basically it sort of embeds, you embed it into each pier, and then that acts as the link beam, if you will, or the coupling beam. So yeah, it potentially can save some money and some time for the contractor by not having to place all that very complicated reinforcing steel at every coupling beam location.
Thank you very much. The next question is, lateral displacement sometimes control the design. Do you feel that the use of the CD factor of the ASCE code to estimate inelastic displacements is correct? Studies suggest that should be higher, close to the value of the reduction of the factor R.
Right. Yep. Nope. It's a good point. So yeah, there's a lot of obviously there's a lot of technical literature that says that we shouldn't have a CD factor less than the R factor. And one thing though that we have to recognize is that in the ASCE 7 building code, the drift limits that are placed on the buildings are not close to the kind of drift that's going to really result in significant damage or the potential for collapse in a building. So if we change the CD factor, we would also probably change the drift limit and effectively end up in the same place. So the two things sort of go together, and I know that's not, it's not a great technical argument, but that's the way that this is sort of built up over time. And the building codes, those factors are 30 plus years old, and so we have talked about that in the committee to revise that, and really haven't pushed it forward. Yeah, it may happen in the future. I hope it does, because it will be more transparent for the engineers to understand. But just recognize that we would also then be allowing larger drifts if we place that higher CD factor.
Thank you very, very much. The next question is, what do you think of dual systems with moment frames and buckling restraining braces so that the frames remain elastic, even in the design-based earthquake, and work as a rendering system? And the BRBs dissipate inelastic energy as fuses. In this case, the moment frames should be designed as special frames or as ordinary frames.
Okay. So yeah, dual systems, they don't get used very often, frankly, anymore. Which I think there's a lot of, they make a lot of sense, because the concept is that you have a stronger, stiffer system and then a more ductile system that works sort of together. But the idea of a sort of a BRB system with a moment frame certainly can make sense. Many times there are some moment connections in BRB frames themselves to make the BRB frame work. So yeah, there are some good reasons for doing that. The other thing that we've looked at, and I kind of mentioned that on the one BRB slide, is this thing called the strong back, where the strong back is an elastic sort of element that's very stiff and requires that when the earthquake shakes the building, that it basically stays sort of linear and doesn't have a kind of differing inter-story drifts during the earthquake. And that kind of keeps the deformation demands in the yielding system, whether it be a BRB or a moment frame or a regular brace frame, to be very uniform, and then you'll get better performance. So that's kind of a hybrid of a dual system. But yeah, I do think there are some good concepts there where we can use a very stiff elastic system combined with a more ductile system.
Thank you very much. The next question is, do you have any advice for young engineers interested in structural design? This is from Diego.
Advice. How long do you have? Yeah, sure. I think that you want to try and expose yourself as much as you can to real buildings and go to construction sites and see what's being built. Use the internet to look at unique projects and try and understand those systems. Talk to your professors and learn about what the best courses to take for structural design are. And then, if possible, what we call internships in the United States, when you're, maybe in your summer breaks, to get to work and see how an office operates, and see the kinds of things that actually get done in the design offices. That would be very helpful to you as well.
Thank you very much. And one last question. Thanks for the great presentation, Jim. Do you have a project that has been your favorite? This is from Danielle.
Oh, okay. So my favorite project is probably that Caltrans project that I mentioned and went through. It had every element in it, and the project is a number of years old right now. And so whether it was the analysis techniques that we did and trying to model the fracture and the connections, which was a very new thing to do at that time, the testing program that we put together, all the analysis that went into it, and that was a unique project because as a retrofit project, we were actually hired. The structural engineer, I was not working for the architect. The architect was working for me, and so we were the prime consultant. So we were working directly for the owner, and that's a very different situation than we have in most projects, where the architect is working directly for the owner and then we work for the architect. But because it was a seismic retrofit, we had the primary role on the project, so they made us the prime. And it's very different when you're doing that, because you can communicate directly with the owner about these seismic issues, right? And stuff that's really important to us. And that's very gratifying to have a client that is values that and thinks that's important, and so that's probably my favorite project that I've worked on.
Thank you so much for your presentation. En reconocimiento por parte del comité organizador. And we thank you so much for this presentation, and we will offer you a recognition from the organizing committee. Thank you so much.
Thank you very much. It was my pleasure. Sorry it went a little long.
Thank you very much, James.
Thank you.
It was a pleasure to have you here.
Thanks, Fernanda. And thank you to Fernanda for all her help in organizing this and making sure I was here on time and everything. So
Thank you.
Thank you so much.